Hi everybody, we're gonna go over some more of our algorithms and try to determine the complexity of these algorithms. So one of the ones that you'll see, I just discussed linear search in the last video, and there we saw the linear search was about, so let me repeat the conclusion. I'm not going to go to the details anymore. We saw that linear search was O(n), where n is the length of the list that where we sort trying to find the element in. So now they have this procedure called binary search, and I'll remind you how it works. We have this list here, and let's put the list, like, think of it as elements that are put here on. So here is A1, here is A2, here is A3, A4, and so on. Yeah, I shouldn't perhaps draw the line. Let me get rid of the line here. So we have these elements here, and we have n of them, and we're trying to find, so as always, let me write it already here. So the procedure is called binary search, bin search, let's call it a bin search, and it consists of a list, an element x, that's an object, a number, I'm gonna search the object, and then let's call it, yeah, no, okay, and then A1 to A2, that's up all the way up to n, is an ordered list, a sorted list. That, of course, is a big assumption, and we will talk about sorting. How do you do that actually? And you'll see that it's actually also not something that one can just take for granted. But okay, so this is a sorted list, and the question is to find x where in the list is x, if it's at all there. But we assume it's kind of there, and we need to know which in which drawer is it. Think of this as a drawer, in which its location is it. Okay, and so what it does is you say, okay, so we cut halfway, and this gives us two groups, and now we're gonna, so here it's halfway, so we don't exactly know what that is. I'm not gonna name them anymore. So we have a bunch of guys on the left and a bunch of guys on the right, and now we take our x and we compare x with, it does a little bit, we can be a little bit free in our choice here. I want to do the, let me go quickly find which choice they make. Okay, they choose the, yeah, so they're asking if you take this element and they compare x, is x bigger than this element? So compare this element a, whatever this element is, less than x. That's the comparison that you do. And then there are two possibilities. Either the result is yes, x is bigger, and then so if this is yes, then we know we have to concentrate on this group, because x is somewhere in that group. They are ordered, right? If the answer is no, then we know we should concentrate on this group and repeat the process. And that's until how long? Until the list is empty. Sorry. Until you have only you keep dividing until you have only one element left on either side, and then you just compare it with that element. Okay. So that's how the procedure works. Now, again, there are different ways on implementing that. I don't remember exactly anymore how I did this, but I think it's pretty similar as to the book. So let's just take the algorithm as described in the book. And what we want to do is this. So you have to think a little bit always, not just what happens at the first step, but at some step. So at some step, we are looking at as part of the list here. So we have already ruled out it cannot be there, cannot be there. And what we then do is divide this list in two. And we take then this element and compare x with the element that is located at that position. So what we need to know, we need to keep track of the positions of the beginning and the end of the list that we still were looking at. And this is what the I and J, so let me call them big for beginning. The book calls them, let me write it again, sorry. Book calls them I and J, but I think it's better to give them some, no, okay, I call them I and J. No, I'm going to call them begin and end. So the idea is the beginning and end are two indices, two locations of the beginning of the list and the end of the list. So of course, when we start the procedure, we look at the whole list. So the beginning is the beginning and the end is the end. But eventually we're gonna whittle down. We're gonna always take. It's like, I don't know if you ever. There's a game like this where you have a square that you draw in the sand, and then you throw a knife or something that sticks in the sand, and then you cut the thing in half, and you keep, and then you choose one, the one that throws, choose one of the sides, and then you keep cutting the next side, the next one halfway, and you're trying to always get to choose a side. Or it's the other guy that chooses, I forget now. But the problem is, what I'm trying to say is you keep cutting down in halves and halves, and you're always working with a smaller and smaller collection. Okay, so here is it done with a while loop. So while, and what we do, remember what we're going to look is, we keep doing this dividing up until we are actually left with a single element in the list. So this, when would this happen? If begin is equal to end, right? If the beginning of the list is equal to the end of the list. So while it's not the case, while they are beginning is not equal to end, or while beginning is less than end, because of course that's also okay. Let me write it that way. Perhaps it's more telling, right? Because the beginning, of course, is always less than the end. But if it's strictly less, then that means there is like 1 and 3 say, then there is still a couple of elements in there. It's only if they're equal to each other, then there's only one single element. So while that is the case, I'm going to divide in two. And that dividing in two is, the location of that is given by this quantity, beginning plus end divided by 2. In other words, I take the average of beginning and end and divide by 2, because I need to take a floor here, because this could be an odd number, beginning plus end, and then I get a decimal fraction, right? And I don't want that. So that is a small little thing that we do, but let's not think too much about this. And now, what do we do then? That's what we next. Remember, I said this is therefore this location here. That is M. The M will mark this point to the left of our cut, and now we're going to compare X with that. So if it has to be still at the same indentation here, it's within the while loop. If X, oops, that's not what I wanted to do. If X is bigger than AM, then that if we compare with this guy, or on this location, the guy that's sitting in that location, if that is bigger, what we need to do then? Well, if it's bigger, then we have to look at this group. Means that we're gonna keep the same endpoint, but our beginning point changes. Okay, then the beginning. What is not the beginning? Well, it should be the location following this M here, the one next to M, right? This should now become the beginning, so that is M plus 1. Else, if that's not the case, what do we? Then we are just in the opposite case. Then we have to search here. That means that the beginning stays, but the end is now, and then end becomes M. Okay. Good. This is. He keeps doing this until he has whittled down to a single element. That means when the beginning is the end. And now that's the time that we say, I'm going to see if this is X or not. If it's X, yep. If it's not X, X was not there. So this is one more if, but this is outside the while loop. So if, so then we have if X is A, okay, now A beginning. But that's the same as A end, because remember, when he stops, beginning and end are the same. So I'm looking at that element, that is A index beginning, the element at location beginning. If that's the case, then, then I put the location is the beginning, or end, it doesn't matter, right? They're both the same. If that's not the case, well, that means there was no element, so else, sorry, not X, location is 0. And then that's the end of the story, and return location. Okay, this is how it the algorithm is. Now let's analyze its complexity. First of all, we have these two initial steps. They take only the two basic steps. And we know now, there's the while loop. That's going to be really contributing. That's going to be the juice of the meaty part of the algorithm. So I'm going to wait a little bit and see what comes afterwards. Afterwards comes an if, then, else. Again, there's only one thing they're doing. I'm going to make a comparison and then either declare it to be this value or that value. So this, you might call this one step or two steps, so two steps again, and return, I don't even count. So it really comes down to the while loop, and let's now look inside the while loop. How many steps is this? Well, this is a step. As a calculation, let's consider this as one single calculation. Arguably, I have to add two elements, then I have to divide, and then I have to take even the floor of that, but we can consider it as a single step. Then we have to do a comparison, and again a declaration. So this also counts for two steps, right? One corresponds, so two steps here, one step here, so the whole thing is 3 steps. So the whole question is now, how many times do we carry out that while loop? Okay, you might try to guess and say, okay, n times, right? You have to keep dividing. Is that really true? Let's see how many times we have to divide if we have 8 elements. Okay, 8 elements. So first time I divide there. And so I'm just making up a scenario. Okay, let's call, okay, I'm going to give some names. So 2, 5, 7, 9, 11, 12, 14, and 16, and x is 12. So I'm looking for 12. So the first time I divide it in 2, I compare 9 with 12, and from that it's clear that it has to be in this list. So I have adjusted, the endpoint stays the same, the beginning point will now be position 5. Clear? Okay. So I divided this list in 2 again. So let's count how many times I'm doing the list, right? So this is the second division now I'm doing. So the first time, second division. I'm comparing 12 with 12. Oh, okay, it's equal, but at the moment I'm just taking is it bigger or not. It might be silly, but that's not, remember, you cannot hope that you sometimes get lucky. You just have to assume we have to do this general case. Okay, so 12, yes, so we means so the test this time comes out, so it means we have to ignore those guys. Okay, why do we do that? What does it mean? It means that the endpoint is now changed, and endpoint becomes now position 6, and beginning point is position 5. I don't write it out because I hope you see it. Okay, we still have beginning and end is different, so I divide in 2 again. So this is the third time I did this, and now I compare again 11 with 12, right? And I say no, it's not. So it's not in here. So that's the conclusion. This is what happens after I have to do this check here, right? I'm doing each time this check. So I'm left with a point where the end and beginning are the same, namely position 6. And so the while loop says, okay, I'm done. So you guys do it now. And he said, and here we now look, is this element 12? Yes, it is. So put location equal to 1, 2, 3, 4, 5, 6. And that's it. So how many times did I divide? 3 times only. Not 8, but 3. Where does that come from? You can try to do this with the same, with a little bit bigger size. Now, why did I choose 8? Because it comes out nicely, right? I keep dividing and it comes out 1. If I do 7, I would have 1 with 4 and 1 with 3. So it's nice to have something very even number, you would say, but not after divide, it should stay even. So I'm actually taking powers of 2 makes it really nice because you keep dividing and you can always be able to divide. So the next power of 2 I could look at is 16, and I'm going to go very quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's do it in 2, 2, 4, 6, 8. So the first division will happen 2, 4, 6, 8 here. So 1 division. It's one of the 2 sides. Let's say it's this side. Okay, I do 1 more division. Do the second division. I compare, and it turns out to be in the second one. So this is out. Okay, I have to divide again. So third division. I compare, and it turns out to be in the first one, say. I still have a list with more than 1 element, so I have to divide 1 more time. And let's say I rule this one out, and now I have to compare with this. It's either this or it's nothing. And see how many times I divided? 4. So let's see. This was 8, was 2 to the power 3. This is 16, is 2 to the power 4. So it's actually this exponent here. So how we analyze this? So the way to do this is we say, okay, I'm gonna make an assumption that might be a little bit silly, but kind of assume that n is a power of 2. You might object and say, wait, but most lists are not going to be that. You have to be lucky to have a power of 2. Okay, suppose it's not a power of 2, then I'm going to add a few things, let's say in the beginning, zeros, if it's numbers. And I know that they're never going to play a role, or an element that's, or something. I put something there, I fill it up with stuff, with zeros, with perhaps numbers that I know are not there. So, but keeping, of course, the order. Make sure that everything is ordered. And that is adding dummies, filling up with zeros is a very common practice to make the size the way you want it. And you might say, but you are now making the problem longer because you're putting more things in there. And the beauty of it is that the complexity does not change. Okay, the number of steps, true, might be a little bit more, but the complexity, and that's why we're talking about, won't change. So I'm assuming n is 2 to the k, and from that I figure out that this while loop will be carried out exactly k times, because each time I have something of size 2 to the k, I divide it by 2, it gets size 2 to the k minus 1. Well, one of the two sides, both sides are of that size, and it's only one of them I have to look at. And I keep doing this, and each time I divide by 2. So only k times I have to do this loop. So this loop will be run k times. That means the whole complexity of this whole thing is just 3k. Right? Because each time the loop is carried out, it has to do 3 steps. So the conclusion is that the complexity here, so the complexity is, let's work it out, it's 3k plus 4. Okay, but what is k here? We should answer in terms of the size of the given data, and we haven't really discussed this either, and perhaps we'll come back to it. What is n? If we say the complexity, what do we take? The size of the input, the length of the input? It really depends a little bit on how you see the problem. So here we took the length of the list, so n. And so sometimes it might be that you have to compare the complexity in different terms. The terms of the size of the list, the length of the list, or the size of the numbers in the list, for instance, could also play a role. I'm not going to go into these details. As I said, this is just an introductory course, right? We're going to take very simple things. But I have to answer in the terms of n. Okay, so I have to link k with n here. Well, this is the formula. And how do you get k? Well, logs, right? Take logs. The log of n is k. Of course, remember, logs are always log base 2. So we get here, this is 3 log n plus 4. So what is the O of this? That is just log of n, because we remember this, we know that this is always smaller than anything else. So this is the dominant one. In the sum, you have to take the maximum. So this is the dominant one. That's 3, doesn't play. So O of log n, which, by the way, is much better than O of n. You might think, oh, okay, n of log n. If n is a million, okay, big number, log of n is way, way smaller. It's about, I don't know, well, I don't actually know how much it is. I think it's 20 or something like that. So it's really big difference between a log of a number and the number itself. Log n is a very, very slow function. It goes very, very slowly. So that's an improvement, but it came at a cost. We needed to have a sorted list. So perhaps we should now look at sorting algorithms. We also saw 2 of those. We had sorting. And so here, this is very interesting because this is a problem that has been very important. For the following reason is also, if you have a list and you have to look for an element in that list only once, the cost of sorting the list first and then looking for the element is not worth it. So you just use the linear search algorithm. But if you have to do this searching constantly over and over and over and over again, like for instance Googling, when you Google whether a certain search term is in the database, and then in that database with the search term, or then the hundreds of URLs that have this search term in it. So there you want to sort alphabetically or whatever way you sort. And by the way, it's not really alphabetically, because if you put in an article like the, I want to find out the dolphins, he's gonna ignore the. So he's not actually putting it. He's not gonna look under T. He's gonna look under dolphins. Okay, so just, but that's a practical considerations. But I'm just saying, you want a sorted list, and then you want to search in that sorted list. The sorting is a very important thing. Now we have seen two things. We had seen the bubble sort. So the bubble sort was, let's do this again on the picture. What we do, we have say a couple of no, let's call this K, and here is A, and let's call this D and E. Okay, so the purpose is to order them alphabetically, and from the heaviest one down and the lightest one up. That's the bubbling. The light one should bubble up and the heavy one should down. And so what you do is you start with the top of your list and you compare it with the next element. And if it needs to be switched, you switch it. In this case, we don't need to switch, so nothing happens at this stage. Now we have to switch these. Then we compare this with that. Yes, this needs to be switched, so we switch them around. So we go down. So this is now the new element that we have to look at, and its successor, the one below it. So we're comparing these two, which again have to be switched. And now we take this element. So we go down in the list, but you see, it could be the same element because the element is syncing at the same time as we keep going. And this time, and one more time, we have to sync. We have to twist, sorry, we have to change. And this is the first run. And by this first run, we know that the heaviest element has now fallen to the bottom. So we know that this part of the list, this part down here, is fixed. So we only have to list this, we only have to take care of these guys and do the same thing. We compare B and A. Yes, they have to be switched because B is heavier. B and D, do they have to be switched? No, there's no need to switch them. D and E, so this is the result. So, okay, so we're comparing this. Now, the next, we have to compare D with E. Do we have to switch? No, we don't have to switch. Oh, that's not a good choice, I guess, because there's too little switching here. Let me make C. Let me make this C here. Okay, that doesn't make this. Nothing has changed here, right? Nothing. I hope you see I didn't change anything. But now these two has to be switched, D and C. So I get A, B, C, D. And what this means is now also D is in its place. So really, we should have put a K underneath of it. So I'm going to do this now. But the K will never be, we never will touch the K anymore. And now we have also the D, correct? And we have to keep going. Now, you say, oh, ABC is done. So why are you going? Yeah, we see that, but the algorithm doesn't know that. It keeps going. Okay, so let's analyze it in the way I described it, rather than just looking at its pseudocode. What do I have to do? I have a list. This list has n elements, not 5, but in general n elements. And what I'm going to do, I'm going to take I'm going to loop from 1 to n. This, and I'm going to take the element that's on that position, but the position, the elements might change. I'm reordering the elements as I go along, right? So once I did this a comparison, I switched these two. So now this was looking at the first element. Now I'm looking at the second element, which happens to be the same as before. But then you show now when I need to, these two have to be switched. Here we didn't need to switch. Here we have to switch. We switch, and we now the next step is looking at the third element, which is now actually the same as the previous element because it has sunk down, and so on. Okay, so if sorry, let me not write the n there. That's a bit confusing, perhaps. Let me say it this way: list has n elements. Okay, so the very first time, how many times will I carry this out? What is the thing that I do? I switch them. That's considered a basic step. Perhaps it's not really. You have to take one, put it in a vault for a sec, and then make the next one. And it's a little operation, but it is a fixed number of steps. So I'm going to consider this as one single step, switching two elements. And so many times do I do this? Well, 1, 2, 3, 4, 5. Actually, n times. So this is carried out n times. What about the next step? Well, I have a list. I don't have to list at the full list anymore. I can now forget the last element. So this is now a list of size n-1. But it's the same procedure. So now in the list of size n minus 1, I have to go look at all the various positions, right? Like almost like a diagonal, right? So each time I go down, so how many is that? N minus 1. So I have to do n minus 1 comparisons and switching. I agree this actually is not 1. I have to compare and then I switch. So perhaps I should say twice. And here the same. So the 2 comes from I have to compare whether this is bigger than that or not. That's one comparison. And then I have to switch. That's another basic step. That's how I come to 2n. And here I get to 2n minus 1. Now, okay, in this particular case, this algorithm is can say you're done, but the algorithm doesn't know. So it will keep going. It will now work with the list of size 1 less. So with this list, and it keeps checking again, checking here, and of course it's not doing anything, checking there, and then, so this is now n minus 2 times he has to do this, and always less and less. So we see that the number of steps, is the sum of, let's write this out. So it is 2n minus I for I going from 1 to n. How do I get there? Well, from I going from 0 to n minus 1. I'm sorry. Well, the very first time I do 2n, so I don't subtract anything from n. The next time I subtract 1 from n. So this is, okay, I0, it depends a little bit on how you write it. If you want to go from 1 to n, let's perhaps stick to 1 to n. Okay. Let's see, can I do this? Yeah, okay, for 1 to n, but then I have to adjust this guy here a little bit, right? I have to make sure that this comes out the right number, plus, then I have to do plus 1 here. If I do it this way, let's see, the very first step, so if I is 1, what is this quantity then? It's n minus 1 plus 1, it's n. So this is exactly that quantity. If I is 2, the next step, this is give me this number, well, n minus 2 plus 1 times 2, yeah, that's that number, okay? And it's all of these, and I keep going until I don't have anything left, so from 1 to n, or from perhaps from I to 1 to n minus 1. Now, in the homeworks, I already discussed this, I think, or was it, or did I forget now? We've already seen a case like this. This is, you can do different things with it, but we can think of this is, look, if I write down these numbers here, right, and this is in descending order, but let's look at the same sum, but in increasing order. Where is it, what was the lowest that I would start was from 2, right, and then I would have 4, and then I would have 8, and I would go all the way up to 2 to the n, right? So I could also write this sum as from 1 to n, 2 to the I, where I goes from 1 to n, right? This I'm running to this list, to n minus 1 to n minus twice n minus 2, twice n minus 1, and so on, downwards. But instead of doing that, why don't I sum upwards? And well, the last one is going to be the last. It keeps always going down by 1 here, so by 2. The number itself goes down by 2. The last thing I will have 2, and then I of course have 0, but that's no, we don't have to add it anymore. So we start with 2, 4, 8. No, 2, 4. Where did I get 8 from? 2, 4, 6. Right? 8, and so on. And so we get twice 2i for all I summation. So it's the same as this thing. And this we have a formula for, that is n times n plus 1 over 2. That's from the tables. And go look up the tables in summation, the steps on summation. And of course, if we can simplify this a bit, this is n times n plus 1. So this is n squared plus n. But the O is just therefore n squared. Right? Because it's degree 2, so that's the O of n squared. So the bubble sort takes O n squared times to do. Now, I didn't give you the algorithm, I did the pseudocode, and in the pseudocode you would see a similar thing happening. I'm going to leave that for you to check. I did it on the explanation. And I'll do with the next one, I'll do it with the pseudocode. So the next sorting that we had was the insertion sort. So insertion sort. And I remind you again how that worked. So now we write our list horizontally. So we have, say, let's take a little bit same list here. B, A, D, C, K. B, A, D, C, K. And what we do is we say, okay, I'm splitting the list in. Originally, I take just the first element, and what is now to the left of this divider is sorted. Yeah, sure, because there's only one element. And then I take the element that is to the other side of the divider, and I'm gonna bring it. If you think of it as here, this is the house. Okay, here's the house, and I'm gonna bring it inside the house. A can go into the house, and he has to go sit in the right spot. Where he has to go sit? Well, he has to sit there. So in the second step, we have this. Okay, now D has to come. D can go in the house. Okay, take your seat, Mr. D. D says, okay, I belong here, so I'm going to sit there. So A, B, D. And then we have C and K left. So now C has to go. So C. Now, how does it... we see... Sorry, C and C. We see where C goes. C goes here, right? We say, oh, I know my alphabet. C goes there. But how would an algorithm figure this out? What does an algorithm do? It says, okay, this is C. I'm going to see. Is C smaller than A? No. Okay. Is C smaller than B? No. Is C smaller than D? Yes. Oh, then C has to be here. Okay? So keep that in mind. So A, B, C, D, and now K. And now K has to be decided where to go. And how does that work? Well, we know where it goes, right? Because we see it. But this is because it's small size. Imagine this is a size 1,000,000, and we have all these words, English words that we have to put in there, or even... Now, let me get this something that's perhaps more telling. A YouTube URL consists of, 16, combination of 16 characters, which are either uppercase, lowercase, or underscores and numbers, whatever it is, and we have to order them alphabetically. Well, okay, then the question is where the numbers go, but there are conventions that say numbers could go before letters. If you look in a dictionary, that even happens there also. Okay, so then it's not obvious at all anymore where it goes. You really have to carry it out. So what it has to do is K has to say, am I bigger than A? No. Yes, I am. So am I bigger than B? Keep going. Am I bigger than C? Keep going. Keep bigger than D? Keep going. Oh, there's nothing else, so that's where I belong. That is how the sorting, the insertion sort goes. Now, think a little bit about it before we pause the video and think of it. What would the complexity be? It seems like if you look at it, what I wrote down here, had to write down many more steps. Remember, I didn't write out all the steps here, right? Because the list was sorted, it kind of got a little bit boring, but you see, I should have gone a little bit more here, right? But here I seem to be much shorter list. So, and this brings me to another thing, as I said, it depends a little bit, what are your complexity are you measuring? The number of steps or the number of memory locations that you have to take? And you see, in some sense, this seems to be less memory, although not the way you implement it, comes down to the same. But, what do you think? Okay, let's see what, let's look at the answer. I'm actually going to give you the algorithm in pseudocode, so the procedure. I copy this just from what we did in 3.1. Insertion sort, insert, okay. And so we have a list of numbers. They say they're real numbers here, and they're real numbers, and they have to be sorted. But as I already mentioned, they don't have to be real numbers. Anything that has can be ordered, like words in a language or search terms and so on. Okay, so the first thing we have to do is we have to loop, and the loop, remember, is what is that we're going to loop? We're going to loop. We look at the second element and try to put it in. Then we look at the third element, bring it inside, fourth element, and so on. So that's the loop. So it goes from 2 all the way to the end. So that's for J. The index here is J. I don't know why they took J, but I'll keep the same notation from J to N. So remember, this is at this point here, J was the fourth element. We're looking at the fourth element and trying to figure out where it goes. And what do? Well, we're going to try to find its position in this list. So we're going to go through that list one by one. So we're going to loop again in that list. That might be something that you, when you were thinking about it, have forgotten, that we actually also have to loop through that list. So that's another for loop, although in the book they'd use a while. So I'm going to follow the book. So while, but if you do a while, there's no counter, right? So you have to kind of bring up a counter. They call it I here. And so while ij, now ij, remember, that's the guy that we're looking at. I'm going to compare, and now I'm going to, I is going to be one of these. So in one of these, so if I is 3, say, inside this thing, if I is 3, I'm comparing myself with this guy. So this is I equals 3. Then this guy, which is j equals 4, when j is 4, this guy will be compared with this. So that's if aj is bigger than ai, right? So if aj, this guy, is bigger than the one that I'm currently looking at, well, it could have been this one. If you want me to do that one, I can do that one too. I'm comparing with self. Am I bigger? If I'm bigger, then what should I do? Well, I have to look at the next one in the list. Okay, it could be that there are more elements in the list here, right? So remember, this is a very small sample. So how do I go to the next element? Well, I increase my counter. Remember, this is the counter that let me walk through this list here. So I increase I, so while I is I plus 1. This is how I keep going until this condition is no longer satisfied, this condition. And what does that mean? It means I found my spot. That means that I have to now insert aj at the ith spot. So, and here I'm going to cheat a little bit. I did that last time also. Now is I say insert. Sorry. This is sorry. This is not in the while loop, but it's still in the for loop, right? Because I have to do this many times. So this is the position is wrong. So here it goes. Insert aj at the ith spot. Now, in the text, they work it out, and there's a little bit of 2, 3, 4 calculations that you have to do. And it's true is that it is yeah. The number of steps that I have to do actually depends on where I have to sort it, because I have to move everything up behind it, right? How do you insert something in a particular position? How do I insert what? How does it work if I want to put C in here? What do I do? Well, I have to say, okay, C, you become now the third element, and D, you become the fourth, and K, you become the fifth element, which you were already, but okay, we didn't know that. So it means involving everything that comes behind after D, everything that comes after here has to be rearranged. Sorry, I'm sorry. K doesn't play a role here. So sorry, there's a little bit too few here. Let's say we have A, D, E, R, F, and no, not F. That would be in the wrong spot. So this is already on the right spot, and now I have to decide where does F go. Okay, and I found F has to go there. So what I have to do, I have to put F here and then shift these two one up there. So the size of this group, that's the number of steps I will have to do. How many are left, that's the number of steps I have to do. So how many are left here? Well, the difference between J and I, right? So this takes about J minus I steps. And then actually plus 1, because I also have to put AI on its spot. That's a small thing. No, I'm not consider this. So J minus I steps to do this insertion. That's annoying, because how can I now analyze this while loop? This depends on a number of steps. Now, I'm going to first do something that perhaps is not correct, but I'm going to say, let's assume that I can do this insertion in one basic step. I have trained my program to do this. I've set this up, so this becomes one single step. It's not true, but that helps me perhaps understanding what goes on. So I'm going to do this. I'll do this in a different color here, where I'm like guessing a little bit. So I'm saying instead of G minus 1, I'm going to see this as a single step. Okay. Right, no. Yeah, okay. So let's analyze everything. What do? Well, we start with a loop already, and how many times we loop? We loop n times. Well, is that true? Yes, it is true, because nothing is bringing us out of the loop. The loop has to be carried out completely. Then we do this one time, this guy. This we said now is one basic step, this insertion, although it's actually not, but let's see where we get. And then finally we have to look at this while loop. So the while loop itself, there's one basic operation we do there, just one, and but the question is, how many times do we carry out the while loop? Now that is a bit of a question we cannot really answer, because it really depends on when is this element that they're comparing with, when does it hit its spot? So here it is after 3, but if we would have to do it with D here, that would be all the end of it, right? It really depends on how many, the actual order of these things. So we have to come up with a worst case scenario. Now the worst case scenario would be that the elements that I have to put in are all the way in the back, have to put them in. When would this happen? For instance, if the list was already sorted, it's very strange. If this would be a sorted list, this procedure would be the worst to find the sorted list. It's there, but it doesn't know it. So it's going to check it, and it's going to take it, because it will each time, if it has to go where this is my element. So here's the sorted list, right? And so at some point you have already D sort, and now D has to decide where it go. Well, we know it has to go there, but it doesn't know it, so it has to go to the whole list that we already have sorted to find out, oh, actually I have to go to the back. So worst case scenario is this will take how many steps? Well, the length of this inner list, and this, remember, this inner list has length. What's the length of this inner list? The length of this inner list, that is given by n minus j, right? So when j is 2, the inner list was the left list. Sorry, inner list. I mean inside the house. So this is j is 2. Then we have one element in there. If j is 3, we have 2 elements in there. If j is 4, oh, it's j plus 1. Okay, so j plus 1, or j minus 1. So j minus 1, right? Yes, yeah, j minus 1, right? So here, for instance, j was 4, and we see already 3 elements in the list. So j minus 1. So this list, the loop will be carried j minus 1 times. Okay, so how many times this is whole thing carried out then? J minus 1 plus 1 plus, well, here we had j minus I, and I depended also on this position, and therefore worst case scenario is that I had to do here j steps. So 1 is the best case scenario, j is the worst case scenario. Worst is that I have to do as many steps as I can do, namely, again, if I have to go if it's all the way in the beginning. Now you say, okay, they kind of cancel each other out, but we don't know any of that. So I can put either 1 or j here. So perhaps better to say it's j steps. So I'm going to make this j here. So, okay, the while loop is carried out j minus 1 times, at worst. I also have to do this guy, that's 1 time, and then I have to do this insertion j times. So this is the number of times this inside part will, the number of steps to carry out 1 time that inside part. And how many times I have to do this now? N minus 1 times. So, but the j depends on it, so I shouldn't say that way, so let me write down here what we have, right? 2j, we found 2j. So this is 2j, but again, if j is 2, I have to do this 2 times 2, that's 4. If j is 3, I have to do times 3. So what I need to do is actually the number of steps, basic steps, is going to be the sum for j going from 2 to n, 2j. Okay, now we have a formula for that. Well, no, we don't, because this goes from j to 1, so this would be this number, right? Sorry, I put the 2 out. Now we know that this is equal to n times n plus 1. Well, divided by 2. Yeah, but that's if you start from 1. If you start from 2, you shouldn't count 1, so we have to subtract 1 from it. Now, all this doesn't matter, because if I multiply all this out, I get n times n plus 1 minus 2. I multiply this with 2. But this is n squared plus n minus 2. All this little stuff is irrelevant. This is O of n squared. So the complexity is the same, although it sounds a little bit better, because you see there are lesser steps. The worst case scenarios, we really take in the worst case scenarios. Perhaps if you think a little bit better, you can improve it, but no. This is O n squared. Okay, this is a little bit more messy. I'm sorry about that. So I hope you understood this. Let me go one more quickly time over it. So we have to carry out this loop, and this goes from 2 to n. So the question is, how many times do we have to carry out these instructions? One here. This is a loop, and the loop is in the worst case scenario. What does the loop do? It looks for the position of the element that has to, the element that's waiting outside on the door. Right? Think of this door. The element says, knocks on the door, said, I want to come in. So this is where should it go? And it has to go through the whole list of people that's sitting and decide where it sits. Worst case scenario is it has to go to the whole list. So worst case scenario is it goes to the whole list, which at that time has j minus 1 elements in there. Okay, so it has to do j minus 1 times this, this is to go into the list. So the whole thing is j minus 1. Now, once it found its position, it then has to say, okay, guys, this is my seat, and so everybody else that comes after him has to now move to the next seat. So this is shuffling, and how many people? Well, in general, we don't, j minus I people are still left, right? Remember, we have, the I is counting how many, where I'm in the list. And so I am somewhere halfway the list and say, oh, here I have to sit. So you guys, the j minus I, the first I ones I looked at. And now the j minus I ones, the ones left. So, okay, let me make it a little bit on the, so here are all the seats, right? And I found that my position is I have to sit here. So what is the length of this list? At that point, it is j, yes, j, or j minus 1 rather, but that's not so important. Remember, that's, we said that, right? So if j is 4, then the list, the people in the house are everybody before you, so j minus 1. Okay, so j minus, let me say it again. So, okay, we have here, let me make it a little bit more visual. So we have the house, everybody is sitting on chairs here. So here are all the chairs. I'm not going to draw chairs because I'm an awful drawer. And so here, this guy comes in, okay, and it says, okay, guys, I want to sit somewhere. I don't know what this is. It's supposed to be a person, but it's not a person on one leg. So I guess so this way. It looks more like a Chinese character, right? So this guy says, okay, I want to come in. Okay, so find your list. So it goes there, 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 there. Oh, here, I have to go there. Okay, so he found his spot. Sorry, let me get rid of it. So what is, how many, he's number J, the J guy. So how many are inside the J minus 1 that are before him? So now he goes to this list and looks at, this is I here. This is I. 1, 2, 3, 4. It says, oh, I'm actually here. I is 5. So how many are still left? Well, j minus 1 minus I plus 1. You just think about it a little bit, okay? Why the plus 1 or not? That really doesn't matter so much. J minus I. But that presumes that I know exactly what I is, but I don't really know. So worst case scenario is that it actually is all the way here that he has to sit, so that I actually is sorry. Then nobody has to shuffle. Now, if he has to sit here, this guy has to go there, and this guy has to be there, right? So, but suppose in the worst case scenario, it would be that he has to sit all the way there. So this has to there, this has to go there, this has to go there. So j minus 1 of them have to move. So the worst case scenario is j or j minus 1. I'm going to be a little bit loose here, because remember that the smaller terms never matter. So the shuffling itself takes j times. The finding the spot also took j minus 1 times, including this also j times. So altogether 2j times. That was for Mr. J to come in. And now Mr. J plus 1 has to come in. So in total we had to do the first J was 2, so that was four steps before he figured out where you have to sit. Well, probably less, but okay. And then the next one, another 2 steps, another 2 steps. So you get 2 plus 4 plus 6 plus 8 and so on. This is this summation that we have to look at. And now do a little bit of algebra, and we see that this actually is quadratic, and that's the only thing that matters. All these little coefficients and constant here, they don't matter. What matters is that it is O(n) squared. And so these two sorting algorithms are both O(n) squared. And this is an example of an algorithm that is not optimal. But in order to describe better algorithms, we need a bit more material, and this will be discussed in discrete math 2. So, and this is very, very interesting, right? So you can do faster than this, and I cannot stress how important that is. Sorting is one of the most important problems, and a lot of resources and research is towards sorting. I mean, they give an example in the textbook. One of the founders of big names in computer science is Knuth, and he has a 1,000-page book, and almost 2/3 of his book or 3/4 of his book is devoted to sorting algorithms. That shows you that in his vision, those are the algorithms that we would have to need, because this is what all these big databases need. They need to be sorted, and they need to be sorted as quickly as possible. Now, n squared looks innocent, but imagine you have 1 million search terms, which is nothing. If you Google search, it will tell you 1 billion perhaps. So to sort that, n squared, that is 1 million times 1 million. Now these numbers get big, and so about how big these are and how bad this becomes, I will talk in the next lecture, the last lecture on complexity of algorithms, where we'll discuss how are these different complexities, how they really play. But that's for next time.